So hello, my name is Gary Tucker. I'm one of the ambassadors that Camden BRI have. My area is technical development, which is effectively processing. As background, I'm a chemical engineer. I've worked in the process simulation, process modeling and validation part of the business for a number of years. And more recently, I've managed the baking and cereal processing department. The subject I'm going to talk to you about today is process innovation in response to market drivers. There's three areas that I'm going to look at. The first one is about fibre and how we can introduce more fibre into products and how that will have a benefit for gut digestive health. So there's a couple of projects there that I'll talk about. The second area is about mold-free shelf life and how we can use a number of different approaches to extend mold-free shelf life but without using preservatives. And the final area is about energy reduction in baking, and there we looked at a number of different areas that were concerning bread baking and how we can reduce energy usage in bread baking. So the first of the areas that I'm going to look at is about fibre and how that fibre can benefit to the gut digestive health. I think we're all very familiar with the fact that fibre is one of the most important areas for food companies to introduce into food products. I've put a couple of quotes there about fibre, the fact that in terms of new products it's very important, in terms of claims it's very important. Also, there are a number of areas of fibre that are particularly important for health. I've put 5 on this particular screen: improving gut health, supporting the healthy immune system, increasing satiety, hence helping weight management, help preventing constipation, and help maintaining normal glucose levels. So they're all very well recognized benefits of dietary fibre. It's also well recognized that within most countries, the UK in particular, we have quite low levels of fibre within our diet, and bread is one of the very useful products of introducing fibre to the diet. Here's a very interesting graph that came from a European project that finished a few years ago. It's a collection of a number of data sets. They're from different laboratories across Europe, and what this graph is showing us that the dots in black represent bread products made without any bran, or with just the natural fibre that you'd get within white flour. The red dots have 10% bran added to the white flour, and the green dots 20% of fibre added to the white flour. Clearly, on the bottom axis we have specific volume, and where we have 0 fibre, we get a much higher specific volume for bread, which is what we'd all expect. And then as we move to the other end of the specific volume scale, where you find the green dots, that's the area where we have 20% of fibre, we find that you have low specific volume and a much harder bread. So what this plot is telling us is that as we add fibre into bread, so the hardness of bread goes up, which is undesirable, and the specific volume of bread goes down, and that's also undesirable. So some of the areas that we've looked at in terms of increasing fibre into bread have been funded by Innovate UK, and several of those projects have been on sourdough and the way that we can use sourdough as a modification method for fibre. One of them involved Newcastle University, who have one of the many model guts that we have available to us. And within that project, we were able to get extremely high levels of fibre into bread, and also to show that the sourdough bread with high levels of fibre took longer to digest in the model gut than a white bread product. And that's really down to the way that the high fibre changes the viscosity of the material that's in the gut, and so the digestion time increases. And within a sourdough, the enzymes have a very large role in breaking down the fibres, and so we have the very hard fibres that you would expect to get within bran that can be softened so that they're easier to process. And some of that softening process will also convert the insoluble fibres into soluble. One of the key strategies if you are making a bread with a high quality or high amount of fibre is to get the dough mixing to the best quality that you can. Any bread process must start with the dough mixing, and the dough mixing must be optimal. So the first strategy then is to make sure the mixing is done to the best, and also the flour properties are the best that you can get for that particular product. If you have a good quality dough, then the chances are that the rest of the processing will work well and the bread will be of a good quality. In terms of introducing fibre through inclusions, it helps if those inclusions are a similar density to the dough. Otherwise, there could be a danger that they will rise within the dough or they will sink. And then the third strategy that's highlighted is about using the surface area, in that the surface area of the dough is very high, and we can use that to hold high fibre materials like seeds, kibble grains, malted grains. And the benefit of that surface area is that we're not interfering with the internal structure of the dough, so we can put the fibre onto the surface, introduce lots of fibre into the product, and the centre of the product, where we have the structural challenges by introducing fibre, remains intact. The second of the areas where technology can be used is looking at mould-free shelf life. And the areas that we've been interested in is how we can achieve mould-free shelf life extension, but without using preservatives. To start with, I've put down there 4 areas for investigation. They very much follow the HACCP approach. So we start off with looking at the formulation and how the formulation of the baked product, whether it's bread or cake, it doesn't matter, whether we understand what that formulation is doing in terms of slowing mould growth. The second of these is about avoiding the contamination getting onto the surface. Now, it sounds very straightforward, but if we stop mould getting onto the surface, it isn't going to grow on the surface of the product over the shelf life. Thirdly, we accept that there is mould on the surface, and we do what we can to destroy the mould on the surface before we pack the product. And then finally, and this is the one that I'm going to focus on mostly for this particular section, is how we can destroy that contamination when it's inside the packaging. So firstly, looking at the formulation. In a bakery product, we tend to have a bit of a hurdle effect in trying to control mould growth. The main factors that are important are ones such as water activity, the level of acidity as measured by pH, and any preservatives, whether those are added or natural preservatives. And the interesting thing about preservatives is that most of them are based on carboxylic acids, and they work in combination with pH. And it is important to understand that, particularly because over time it's very common for recipes to change slightly, ingredients, the supply chain changes, different suppliers of ingredients occur, and so the properties of those ingredients do change over time. So it's important to understand what's actually in the recipe, and particularly how it affects the preservation. And then the last bullet point I've put there is about salt and sugar, 2 of the very important health areas that most governments have been focusing on. As we reduce salt and as we reduce sugar, we are affecting water activity in our products, and so that will have an effect on the mould. Second area of trying to extend the mould-free shelf life is avoiding the contamination getting onto the products in the first place. If you think of a baked product that comes out of the oven, it's effectively sterile, and I've put the word sterile in inverted commas, particularly because microbiologically they are not sterile, but for all intents and purposes particularly for mold, they are sterile. So everything that happens after the oven will contaminate that surface. So the cook chill industry, when it started up 30, 40 years ago, took the approach whereby it introduced a barrier between a cook process and the packing. And that is one strategy that can be used in baking by having two distinct areas to the bakery. And when the products exit the oven, they go into an area of much higher level of hygiene, and so that will avoid the contamination, or it certainly will reduce the contamination considerably, and hence the mold-free shelf life you can expect to be longer. Third area is using different technologies to destroy the contamination. I've listed some of those that are used. Several of these are very much in the research field, although there are commercial applications for all of these different technologies. Camden BRI has been very active in UV, pulse light and ozone in terms of decontamination technologies. But the interesting thing about this approach, and in fact the previous approach about the barriers, is that once the consumer opens the product, there is no protection to the product, and so the mold-free shelf life will carry on in the usual way as if there was no protective technology. Final area, which is the one that I will just tell you a little bit about the current project, is accepting that there will be contamination on the product, but applying a process, and in this case a thermal process, to destroy that mold. The project that we have is a 2-year project funded by Innovate. It involves 3 companies. The main partners and the lead partners are Everfresh Natural Foods, and their products are sprouted grain bread and cake, and they're all organic, no preservatives involved in their products. Holmac, who would not normally get involved in a bakery product, manufacture, or rather are agents for Lagarde steam air retorts, and that's the technology that's been used to extend the shelf life of the bread and cake products. And then ourselves, Camden BRI, are providing technical expertise in nutrition, baking and thermal processing. So you wouldn't normally expect a bread or a cake product to have received a thermal process. If we take a standard bread and a standard cake, if there is such a thing, and it had no preservation hurdles, we put it in a package, we would expect approximately 3 days for the bread before we could start to see mold growth, and for a pound cake, probably about 10 days. Now that all depends on the actual recipes, the process, and the conditions of packing, but those are roughly how long it would take for mold to grow. The market that Everfresh are in requires products to be exported, and their products go to Australia, to the Middle East, so they need very long shelf life. And that's where the thermal processing step has proved invaluable for extending the shelf life. And the picture there shows the new Lagarde retort that's been installed as part of the project, and a basket, or 3 baskets, containing bread products that are packaged and ready for processing. So if we start with the bread, there's only one ingredient in this bread, and it's either sprouted wheat, rye or spelt. The shelf life needs to be of the order of 12 months. The interesting thing about this product is that it gets baked in a tin, so it has its first process. It then gets repacked, packed into the film, the particular film that is suitable for a steam retorting process, and then it gets a second process. So it's a double process. The advantage of the second process is the package is sealed, and all the contamination within the package that's on the surface of that bread can get inactivated. What we tend to find with the bread products is the sprouting process generates a certain level of sugars, and those sugars drop the water activity down to below 0.94, that's of a big benefit in terms of some of the food safety microorganisms that could cause a problem. And so the thermal process, which is actually delivered to the center of the product, will enable the organisms that might have contaminated the baked product before it's packaged from growing. And that's a very successful process. Cake, on the other hand, is preserved in a slightly different way. There are high levels of sugar in cake, and cakes are water activity controlled. Now, with the Everfresh process, it's fruit juices that are the sources of sugars, but still the water activity of the cake products tends to be in the region around about 0.75 to 0.9. Now, 0.9 is quite high for a cake, but those are the products that we've been working on with Everfresh that are reduced sugar, and as soon as we reduce the sugar in the recipe, so the water activity is going to rise and the mold-free shelf life is going to go down. But that's fine for a product that has a secondary process which will kill the molds on the surface, and so we've been able to generate really quite low levels of sugar in cake products but still retain a very high shelf life. And this is one of the few technologies that will enable that to be achieved. Now, one difference between the way we're working with bread and cake is that the cake products don't suffer very much damage at all when they're removed from their baking tins. And so we're interested in probing those cakes during the secondary process just below the surface. And the process then is applied at that particular point. In terms of where this project is going, already it's been a massive success. The bakery has redesigned 2 new sprouting vessels, and that has increased the throughput of the bakery by at least 50%. And the new retort that's been bought has enabled higher throughputs to match those sprouting vessels. Export numbers for the bread and cakes have been extremely high, and the bakery is probably going to have it to expand again to meet that need. And the interest has been so great that the bakery is looking at some different products, again using the sprouting technology, and that includes falafels based on sprouted chickpeas, burgers also based on sprouted chickpeas, and a sliced bread product that has an 8 to 10 hour bake. And because of all these really interesting developments and the benefits of the low sugar cakes, discussions have started with major retailers about supplying those cakes. The third area of the technology innovation concerns energy reduction in baking. The pie chart that you see on the screen was one that the Carbon Trust produced in 2010, and that shows us where the energy is going when we have an industrial oven. And it shows quite clearly that the flues, which are in the purple colour, have a significant proportion of the energy that goes straight up the flues to atmosphere. The tins themselves that hold the product also absorb a considerable amount of energy. Then the pink section of that pie chart is purely for evaporating water, and again that ends up in the flue. And the red is for the energy that goes into the dough, converting the dough into bread. And then there's sections in yellow and green, which basically are the other areas of energy absorption during the baking process. Our interest was really in 3 of those: the flues, the water, and the dough, trying to look at what we can do in order to cut down on the energy that we use in baking. In order to do that, we had a series of projects over a period of about 5 years, funded by groups like the Carbon Trust and our member-funded research program, in looking at those 3 main areas: flue gases, bake time reduction, and water reduction. And our interest was industrial baking, so we focused on the Chorleywood bread process, as shown by the mixer and the tins in Approva. So if we look at flue gas control first of all, the project with the Carbon Trust also involves Spooner Industries, who are manufacturers of ovens. The flue gases, when you look at the way that a flue operates, they basically have two main components. One is a fan that tends to be fixed speed, and the other is a manual damper control that can be adjusted by the oven operators. The issues that we are interested in is when we change over product, there clearly is a gap in the conveyor of the oven, and while that's happening, the flue fans are operating, they're drawing cold air into the oven, and so that's cooling the oven. Similarly, when the product throughput is reduced for whatever reason, the fans again are operating at the same speed, gases are being drawn into the oven, and the oven cools. Then the combustion chambers have to correct that cooling when the product throughput goes up to the normal levels. That's probably very nicely illustrated by this simple diagram. The diagram shows a continuous oven. It's only got one section. The picture at the top right is of a Spooner oven for baking biscuits that has several sections. That will probably have somewhere between 3 and 5 different flues. And we can see from the direction of the arrows in the schematic diagram that we must first of all draw air from the bakery into the oven, otherwise combustion gases or products of combustion can escape into the bakery, which would be a safety issue. The flue then takes gas from two main sources. Firstly, combustion gases end up going into the atmosphere through the flues, and secondly, the product itself generates gases as a result of carbon dioxide, ethanol, water that evaporate during the baking process. And it's necessary to know how much gas is produced and where it's produced. These bar charts show that. If we look at the bar chart on the right, the bar chart there is showing this that for the 3 flues in this particular oven, there isn't really much difference between the volume of gas that goes up those 3 flues. The bar chart on the left shows us that the first flue that a bakery oven experiences has a very low level of gas coming from the product. But as that product warms up and you get evaporation of carbon dioxide, ethanol, and finally water, the amount of gas going up the flue increases. And if you think about the 3 flues having fixed speed fans, drawing gas up the oven at the same rates, clearly there's an imbalance between what is happening inside the oven and what's going up the flue. And our project was of interest in how can we correct that? So that was the first area. The second and third areas are very much related because you can't really reduce water evaporation without doing something about bake time. And so what we did here was have a fascinating member-funded project where we learnt a huge amount, and we looked at trying to cut down on the amount of water that we put in a bread dough recipe, and also cutting down on the bake time. And both areas clearly save energy in baking. But what was of paramount importance was that we didn't affect the quality of the bread that was being baked, and it had to have the same quality in terms of crust and crumb properties, and it had to have the same water content, because the amount of water in a product is very important for both quality and also for the weight. Clearly there were a lot of technical challenges with that. If we drop the water content in a dough, the dough is going to tighten up, and that will give us problems in moulding and proving and many other the processing steps. So what we tried to do was to accept that the dough is going to be tighter, but mix to a higher temperature and use the fact that higher temperature equates to a lower viscosity, and so we would naturally let the dough soften. And interestingly, that has a number of additional benefits, and those additional benefits, I've listed 3 of them there. during the summertime, when typically a bread dough will be warmer than in the winter, it's common for the high shear mixers to have glycol cooling jackets. Well, clearly by allowing the dough to go to a higher temperature, we can reduce the need for that glycol cooling, and that will save some energy. Also, the enzymic and the chemical reactions tend to work faster as the temperature goes up. And at 35 degrees C, they're working faster than a conventional dough that might be at 30 degrees C. And that increased speed of reaction also applies to the yeast, and so the yeast will be working faster, producing more gas, and so we can take some time off the proving time. Clearly, we've got to be very cautious. Not everything is positive. There could be some effects on the bread, and so we needed to do a lot of adjustments to the process in order to correct that, which we actually managed to do very successfully, and in blind testing we were able to show that it was difficult to pick which breads were made with a conventional amount of water and a conventional bake time, and which breads were made with reduced water and a reduced bake time. So that was a real success. And just putting some numbers onto this in terms of energy saving, I've put down the three measures that we looked at by reducing water, reducing bake time, and looking at flue gas control. Converted it to the percentage of energy that we can save, and then also converted that to £1,000 per year saving. And all those are based on industry data and ovens with the 1,100 kilowatt hour burners, 3 of them, 24/7 operation, gas price of 5 pence per kilowatt hour, and the annual gas cost for a typical large industrial bread oven might be £1.3 million per year. So that gives an indication of the sorts of savings. So some very interesting work that happened in that project. So I've taken you through 3 very different areas where we've been looking at in the baking department. Improving gut digestive health, and there we looked at how we could use sourdough and fibre to increase the healthiness of baked products. We looked at shelf life, very much took a HACCP approach, prevention, introduction, growth and survival, investigated the different methods that we could use, and we focused on one that is a thermal process to the packaged product, which gives shelf life of the order of sort of 12 to 18 months. And the third area was energy reduction, quite different again. We looked at a number of ways of dealing with the different areas where energy is used in baking bread and what we can do to try and cut down on each of those areas. So 3 very different areas. The message really is, if you've got any areas that you're interested in looking at and investigating, let us know. We're always very interested to discuss industrial issues, discuss problems, and help work up those ideas and find the suitable ways of funding that work. And you've got my contact details there.